So when figuring out what if it's increasing or decreasing, you're going to check the rate at 20, and since the function was already a rate of change, we can just plug in 20, and this number happens to be negative. If a rate is negative, this is our graphing unit, we know the original function was decreasing. According to the model, how many mosquitoes will there be at time 60? So we started with 1200, and then if you integrate from 0 to 60, that will be the change that happens. And this, of course, you would just plug into your calculator. You have the 1200, type this into your calculator to get 282.272. Add this together. This is roughly 1,482 mosquitoes. So again, units are going to be important. In these questions, we need to know what we're talking about. So when we write our answer, we write mosquitoes. So notice how I kept the 3 decimal places to show anybody who's like, yes, I've kept my accuracy there. But since we're talking about mosquitoes, I rounded to the nearest whole number. And then in part C, it does say to the nearest whole number. What is the maximum number of mosquitoes from 0 to 60? So what do we need to find out? Do we see that this is finding a maximum is often extreme value theorem, which you have to check your candidate points. Where could this be a maximum? So what I've got here is I've got places where things are equal to 0. So if we solve when is it equal to 0, that's going to be at time 0, at 6 pi, at 12 pi, and at 18 pi. So we would take our original function, set it equal to 0, and since you know that sine is equal to 0 at 0, pi, 2 pi, right, we could just set that this t over 6 has to equal 0, pi, 2 pi, 3 pi, and so on. And then if I multiply each of those by 6, we get each of those answers. And of course, after 18 pi, you're already past 60. So these are candidate points: 0, 6 pi, 12 pi, 18 pi, and 60. Okay? I would really, like in this one, I know that my function's increasing, then decreasing, then increasing, then decreasing. So technically, do we need to check 12 pi? No. Because you know that it won't be a maximum if you've gone down and then back up again. That's true. Although, just because I've seen students lose marks on the exam for this, I would actually check I would check 0, I would check pi, I would check 2 pi, I would check 0, I would check 6 pi, I would check 12 pi, I would check 18 pi, and I would check 60. Of course, we did 60 in part B, but if you don't reference it here in part C, on the AP exam, they might take off a point just like You didn't use the extreme value theorem. Okay, I would probably even in this question say, I want to use the extreme value theorem. My function is continuous. Its derivative exists because the radius is there. So I can use my extreme value theorem. And so then I need to check all my candidate points. And I get my max number is 1526. I find on the exam these ones about max and min are often ones students don't get full marks because they're not showing all of those steps. So as far as figuring out our candidate points, you know you started at 1200. 6 pi got us 1414. 12 pi we didn't do, but I would add it in here and show that it doesn't work. This one's 1526, and we had figured out that 60 was 1482. You could argue, of course, that you don't need to do this because it's going to be decreasing to that point and then increasing after it. But the exam might want you to show that argument. And I sometimes find that showing the argument is a lot less than just saying, let me just do all the candidate points. It's not hard to retype this into my calculator and just change that to 12 pi, quickly get my answer, and then keep going. So showing all the candidate points, showing that you're using the extreme value theorem. Remember, anytime you use one of your value theorems, intermediate value theorem, extreme value theorem, mean value theorem, you need to state that the function is continuous. Did it give this in our question? Right? Well, since the derivative exists, this was something way back in one of our first chapters. If a function's differentiable, it implies continuous. Okay? But nowhere in this question did it say continuous, so they might have taken off a mark in I'm using the extreme value theorem here, but they might have taken off a mark in part C because I didn't explicitly state that my function is continuous. I just assumed it. And they often have a mark associated for that little part. And then Miss LaFrance and I go through the statistics, and they're like, why did our class average 0.01 out of 1 on Mark 4? And we look it up, and Mark 4 was, students stated that it was continuous. I'm like, oh, everybody just assumed that. Okay, area between two curves. You know that the integral represents the area under a curve. And a review, if the area under the curve is above the x-axis, it's positive. Area under the curve, below the x-axis, is negative. Really, area under a curve meant area between the curve and the x-axis. And something really cool happens is now we can figure out really weird areas. So, how do we figure out the area in between two curves? We find out where those two curves intersect. We look at going between those 2 points, and we take the top curve minus the bottom curve. Here is integral form. It'll be really quite obvious when we look at this first example. Or, sorry, you weren't done right? I'll give you guys a couple seconds. While I'm giving you some time, we'll draw a picture parabola like this in black, another parabola over here in green, and we're asked to find that area in blue. Does it make sense that this point A and this point B will be important? In fact, if I find the area under the black curve from A to B, I can take out a highlighter and highlight that in blue. That would be this whole area, right? And then if I found the area from A to B in the green part, under the green curve, that would be this purple part. And does it make sense that if I took the blue part and subtracted the purple part, I would get that little section in between? Area between curves is that easy. It's just the area of the upper one minus the area of the bottom one. Now, if you analyze this and think about this, the question is, well, what if my x-axis, like what if my curves were like this? Here's my black one, here's my green one. Do things get messed up when some of the area is below the curve and some of it's above? Can you see that possibly being a problem because some of the areas were negative? And it actually, guess what? No. It's still super simple. If you did the area from A to B of the green one and subtracted the area from A to B of the black one, it works out perfectly to be the area in between. No need to worry about where there's x-intercepts, where things are positive, where they're negative. It works out beautifully. So this ends up being a really simple idea. If you want to find the area between the two curves, it's just the area of the top curve minus the area of the bottom curve. And you can either, because we have an integration rule that says when you're subtracting things, you can integrate them separately, or you can simplify first and then integrate all together. So notice here in the bottom part, you could simplify them first, or you could just integrate them separately. Both of those would work. And sometimes one thing will be more advantageous than another. I love taking out crayons for this part. Here we go. I feel like orange. Find the area enclosed by these two curves. That is that part right there. So in order to find area between two things, do you see that it's going to be super important that we find out between which two values it is? Once we find between which two values it is, we can integrate the top one minus the bottom. So how do I find those intersection points? Well, that's when those two equations are the same. They would have to be equal to each other. So I can just make the one equal to the other one, combine my like terms, solve, and we find out one is at -2, the other one's at 2. We can plug -2 and 2 back into those original equations and find the points. We don't really need those points. But now we can find the area between by just doing the integral of the top function minus the bottom function. And what's really nice here is instead of doing them separately, things simplify. Like I have like terms in there. I could integrate this one separately and find the entire area under the blue curve. And I could integrate and find the entire area under the red curve. But why not put them together and then I get a much easier integral to do? Especially if this was non-calculator, that's a lot less math. And then I just need to find the value from 2 to -2. You can just type in the answer here. I'm sure you could do the mental math. And I sometimes like to look at this question and think back to our grade 11 selves when you were in grade 11 pre-calculus, which most of you took in grade 10. You could draw both of those parabolas with what you learned in grade 10. And you could find the intersection points. That was grade 10 math too. Or I mean, grade 11 systems of equations. You did that in grade 11. You could find those 2 points. But if I got you to color in that area, and I said, that's a weird shape. Can you find that area for me? Be like, there would just be blank. You'd be like, there is nothing I can possibly think of to figure out that area. That would be extremely difficult. In fact, some of you might say, oh, it's probably not even possible to figure out mathematically. And I don't want to say disappointed. The integration and stuff actually makes this quite easy to solve. And I don't want to be disappointed that it's easy to solve because there's something beautiful in it, and it hasn't been easy. We've developed a whole bunch of math. We had to go through all of those Riemann sums to eventually come up with integration. So it's by no means easy, but now that we have those tools, actually figuring this out is rather simple. And that's, I think, the beauty of calculus. We went through complicated things, and if you imagine what we actually solved there, if you think back to 2 years ago, you'd probably say, I don't know if I'll ever be able to do that. Someone developed mathematics to figure this out. In fact, you can throw together any 2 weird curves you want. Oh, let's put a log graph and a sine graph and find the area between them. You'd be like, yeah, no, impossible. And now it's all going to be super easy. So we'll start off with some boring ones. All right, I went with orange crayon last time. I'm feeling purple crayon. I'm going to need this point and this point. So first, we always need to find out where we're going from. Where do they intersect? Well, you set one equal to the other. We solve, this one is at -1. Over here, this is at 4. We could label these points if we wanted to. 4, 5 and -1, 0 are where these 2 graphs intersect. So if I want to find the area between those 2 curves, I have to do the upper one minus the lower one. What happens if you don't know which is the upper one? Like sometimes these are graphs that you know. This is a parabola that opens up. That's a straight line. If you just drew a random parabola opening up and a straight line, the line would always be on the top. Does that make sense? If you drew a picture of it, you can often tell. If you have a parabola opening up and a parabola opening down, the opening down one will always be on the top if they intersect and there's area in between. But sometimes you might not know which is the one on the top and which is the one on the bottom. And what would happen if you accidentally screwed up and flipped it? Okay, now I'm going to give you numbers. If you had 7 minus 5, you would get 2. If you screwed up and did 5 minus 7, what would you get? Negative 2. If you had 10 and 3 and you did it right, you'd get 7. But if you screwed up and had 3 minus 10, you would get negative 7. So if you screw up, you will still get the right answer, just negative. And I wouldn't say go back and erase all of your work. I would just go back and add absolute values along the way. Technically, you're not wrong. Just absolute value this and be like, that makes it positive, and your answer will be right in the end. If you get to the very end and like, oh, my area is negative, that means I put the wrong one on the top. Don't go back and erase everything. Just like cheat. It's like, oh, I meant to put absolute values around this the whole time. Again, it makes life easier if you simplify first. Simple integration. Don't show all the work. Just write the answer down. We get 125 over 6. The only place, and we're going to get to this later, that you're going to have to be careful. Let's say I gave you an x cubed graph and a straight line, and it asked for the area in between the curves. Then you'd have to do those two areas separately. Because the blue one is on top here, and the black one's on top there. So if you just did blue minus black, if I did blue minus black, this would be positive, but this would be negative, and if you put them together, they would cancel each other out and life would be bad. Your answer would be wrong. So this is the one situation where you have to be careful. If the area between the curves is separated into two sections, and one time the blue graph is on top, the other time the black, and we'll get to some examples. All right, have a great day. Happy Monday.